get well soon. And our final speaker in this session is Erik Rosolowsky, coming via Zoom on the ngVLA K-band.
Thank you very much. Can you hear me okay?
Yes.
Oh, fantastic. All right. I'm going to get started and share my screen here. So I wanted to start out with the standard. Thank you very much for allowing me to be a big screen and talking to you. However, I am actually really sad that I'm unable to get there. It looks like my slides are coming up, but this one's really boring, so you're not missing too much. Anyways, I wanted to really regret not being there. I've always loved being able to spend some time in Green Bank and regret that I can't spend time right now. Yeah. All right. So today I was going to talk about the next generation very large array and its operation.
Sorry, Erik, hang on a second.
Yeah, we're having trouble viewing your slides here.
See your slides on the screen.
Everyone just turn around.
Let me know if there's anything I should be doing on my end.
Yeah.
I would.
Yeah.
Okay.
Yep.
Then, I mean, we see your slides on the room. Just when we turn around to the back, can everyone on Zoom see the slides fine?
Can see the first slide right now.
Perfect.
Yes.
Then we just do that for now and we try to figure it out in the meantime. Just keep going, Erik.
All right.
We turn around. We don't see you on the big screen. We see you on the small. We see the slides on the small screen with you right next to it. We will try to get the beamer to work again.
Okay, very good. Yeah. If I need to do anything, hey, everything's good. Well, okay. Thank you very much for letting me be a talking head for you today. Is the long and short of it. I want to talk about the next generation VLA. I sit on the Science Advisory Council, but I am otherwise not deeply integrated into the ngVLA project. And so I'm basically really grateful for all of the wonderful documentation that the project has made available and the science cases that I've tried to summarize here. And those of you who have been involved with those science cases, feel free to point out amendments and amplifications when we have a chance to discuss this. But the next generation VLA is a proposed new radio interferometer to be built in the United States, Mexico, and even a little bit in Canada. The basic idea is to put 214 18-meter antennas to build kind of a main array and supplement that with a long baseline array to recover very long baseline interferometry capabilities. I'll call that the LBA through here, as well as a short baseline array that consists of small dishes of 6 meters that'll be packed kind of compactly to really sample short spacings for the interferometer, allowing us to recover large spatial structures in our emission. And then finally, in the proposed documentation, there'll be a total power mode that is roughly 4 18-meter antennas that will operate in total power. And you can sort of see that this looks a lot like the ALMA model for doing full sampling of interferometric imaging with a main array, a compact array, and total power capabilities. And ALMA is also aspiring to even ever longer baselines. So the artist's conception of what the dishes look like are these kind of octagonal features here. That's still that a little bit in flux as a lot of the design and testing for antennas is going out and being developed right now. The array itself will be built around where the VLA is now. This is a map of the disposition, starting here with the smallest scale in the lower right. The short baseline array are these tiny little green triangles. It'll be surrounded by a random field of baselines that are kind of the compact baselines. And then on slightly larger scales, it'll fill out into these logarithmic spirals, and then some additional stations that are built throughout the American Southwest and into Mexico. And unlike the current VLA, this is not configurable at all. The antennas will not be picked up from Texas and redeposited in New Mexico anytime. These will be single permanent stations, and we'll be adjusting how we're doing interferometric imaging by changing the weighting of the data and like what we're prioritizing in terms of the imaging process. Are we going to favor the short baselines, large angular scales, or will we emphasize the longer baselines and get to the highest possible resolutions? The longest possible resolutions indeed will be achieved by introducing these long baseline array stations that kind of mimic what's happening with the very large, the VLBA, the very long baseline array, with stations from the Virgin Islands out to Hawaii and then up into Canada to get the really smallest possible scales, really using for non-thermal and high brightness science to get the best angular resolution. So the thing that's kind of exciting about the ngVLA to me is just the frequency range that it's covering. There's kind of this large stretch running all the way from about 1 gigahertz on the low end, covering the H1 21 centimeter line, all the way up to the atmospheric cutoff at about 116 gigahertz, which includes the 12CO 1 to 0 line. And so that basically spans all of the neutral interstellar medium and lots of other exciting physics in between. But by my heart, I'm a spectroscopist of the neutral ISM, and therefore that makes me very happy to have one facility that can cover these two kind of workhorse tracer species that will give us tons of information. And I mean, there's other science too that I'm going to get to share with you, but it's why I'm excited. This particular graph is showing the effective collecting area of the array as a function of frequency. And the reason why it's effective is, and that ngVLA curve traces up and down a little bit, is it's taking into account everything like receiver illumination and spillover and efficiency of the antenna and everything. So it has a bit of frequency structure to it that corresponds to how the array responds to different types of radiation. But the important thing is that the red curve here is much larger than any of the other comparable facilities that we see sort of graphed along the bottom. And I'll come back to this time and time again through the talk, which is the way we achieve better sensitivity for thermal surface brightness limited science is really only through collecting area. We need to put basically more metal onto the ground to do more ambitious science, because that's fundamentally what's going to regulate our sensitivities. The topic of this talk, the topic of this conference is really about the K-band, and so how that intersects with ngVLA is what is called band 4, which covers a slightly different frequency range, but I've illustrated here the 6 different proposed frequency bands across the ngVLA here in these kind of color-coded regions, and then band 4 is right here in the middle, and it spans the frequency ranges that overlap a bit with the current K-band focal plane array there at Green Bank. The frequency overlap isn't perfect, but a lot of the key science that I'll be talking about for the ngVLA and with reference to GBT really happens in this overlap frequency range. The ngVLA is built around a central signal processor, what we would call a correlator for shorthand, and the correlator is going to pull down at least 14 gigahertz of instantaneous bandwidth with a specification for approaching 1 million channels across that. Is going to have zoom capabilities where we can drop little high resolution windows throughout the band. And the minimum resolution is going to be about 400 hertz, according to sort of the current thinking. And that translates into kind of 5 meter per second velocity resolution at 24 gigahertz, which is the ammonia rest frequency for doing a lot of the science that we've seen today. That's plenty. We don't have to worry too much about higher velocity resolution than that. If we actually want to drop those 750,000 channels across the entirety of the 14 gigahertz band, that would give us 0.2 of a kilometer per second resolution while getting literally everything within the frequency band. That would be an intense data rate, but it should be enough to work out a bunch of different science cases. The thing that basically the statistic of merit that's really important for science is embodied in this somewhat complicated graph about the sensitivity of the ngVLA. So here we're plotting this delta S prime metric as a function of frequency and comparing it to several different facilities. So this is adapted from an ngVLA memo. And this takes the radiometer formula for an interferometer and splits it into 2 relevant parts. This delta S prime statistic encompasses everything that has to do with the telescope itself, like what you build goes into this term. So that includes the system temperatures in the observations, the number of stations that you have, the collecting area of those stations, and their aperture efficiency, so how well they're collecting the light that falls on them. So that's basically hardware. You build a telescope, that's what you get, and so then you can compare that to the different facilities here in the graph. And the general sense of it is the larger this number, the more sensitive your facility is, and it scales linearly because this chunk of terms all come into this radiometer formula. Here, this is estimating the noise in flux density units. Basically, it's 1 over delta S prime times the things that you would tune your observation to, which is the bandwidth time product. So basically, how long you're going to observe for and how large of a spectral band you're going to integrate to get one of the resolution elements in your data set. So these traces here, it turns out I'm colorblind, and my spouse came in and really helped me say, okay, indeed, the tall one, the one on the top is the ngVLA. So I put some labels here so I'd remember which one is which. But there's at least an order of magnitude jump up, including the by accounting for, or by building the ngVLA, it's at least a factor of 10, in many places more sensitive than any of the proposed or existing facilities. The curves here are different weather conditions. For clarity, I also put the GBT operating at K-band on here, which is a little bit more sensitive to the VLA, but still there's going to be more collecting area in the ngVLA. And so there is this space where we have to think about what the sensitivity of the current facility is and how it's going to compare to the upcoming proposed facilities. So the other thing that's kind of relevant, especially for Green Bank, is the intention that the ngVLA will incorporate total power capabilities directly into the array construction. So right now, this is under development by a working group that's out sort of developing the specifications and requirements for what the total power capabilities will look like. But in essence, the short baseline array and the core array will have a distribution of baseline lengths shown here in this graph, where this is baseline length on the horizontal axis and the density or number of baselines on the vertical axis. And this doesn't go go down to 0. Just you can't get the short baseline array close enough to directly sample 0 spacing. So you're always unknown as to what your total flux is in the map. So the total power dishes will be large, or will be the 18-meter dishes, but really commissioned for high performance and high stability. And again, there's probably, following the ALMA model here, I think the working group may actually have to ask whether there will be multi-pixel arrays on the total power antennas and what that would look like. But this is all under development. The intent remains strong to have total power capacity. And so one of the obvious synergies between the GVT and the VLA right now is going to come into a point of dialogue here, where it's just not the natural total power complement for the facility. So the current status of the ngVLA is that it's received strong endorsements from Astro 2020 US Decadal, one of sort of the 4 call-out projects for the coming decade, as well as a high sort of recommendation from the Canadian Long Range Plan. The Astro 2020 cited some cost concerns associated with the preliminary stages of development, and the project office is not very concerned about this because the Astro 2020 referenced some values that were preliminary at best, and all of the design work has really pushed the ngVLA towards kind of higher cost efficiency, lower cost, higher cost efficiency to achieve the science goals that they're looking at. So they are highly optimistic that they're going to be able to hit a budget envelope for the entire project. The facility is building international partnerships. Mexico and Canada are possibly hosting ground stations here, and then Japan and Germany are interested in scientific partnerships as well. The intent is to operate the facility under open skies, as per all National Science Foundation observatories, but the science partnerships here would really be to develop kind of core capabilities and to have scientists engaged in the kind of development of the initial sort of key science for the facility. The observatory has, or the project has completed a technical conceptual design review just recently over the summer. So this basically means that they've gone through the design and said that the ideas here are solid, everything seems to be connected up on the technical side, and the proposed solutions should work for achieving the science specifications. This will then get folded into a programmatic conceptual design review that looks at the overall facility and assesses whether the observatory is going to be able to operate. And pending that review and kind of good costing numbers coming out of that, it'll sort of go forward to the National Science Foundation for integration into the large observatories funding stream there. The NSF is providing some support for design and antenna prototyping right now. So the project is being carried forward for the next few years to the point where the next big stages are really, is this kind of the overall go, no go on the project when we go to NSF and to presumably our other partner country funding agencies. The timelines are put here, kind of thinking about a complete design and construction start in 2025, 2026, leading to a sort of 10-year-long construction process with commissioning starting in the mid-2030s. The big question through all of this is that this is intended as a full replacement for the current VLA. And so the question is, what is going to happen to the existing facility? How will those capabilities get ramped down while the ngVLA comes online? And the current status of that is that there is a panel that's been selected to start reviewing these options and what's the cost of running a VLA while building an ngVLA what key facilities can we not afford to lose until those are replaced by the ngVLA, especially with respect to other operating observatories. So these are open questions right now. And so that question, that 2030 is entirely a variable sliding scale with different kind of capacity probably turned on and off at different times. Actually, it's an interferometer, so you can start operating parts of it and commissioning parts of it without necessarily having the full facility completely constructed. So there's a bit of a soft ramp, and these are not really delta functions in terms of events, but this is a long continuous project with sort of core science operations planned for the middle of the next decade. I think it's worth noting the comparison to the other big radio observatory that's being built right now. The Square Kilometre Array is nominally well into construction at this point. For the purposes of K-band, that's not really the SKA anymore. There was an idea initially to have a high frequency component that would run up to about 25 gigahertz. This has now been essentially designed out of the facility, and they may reach up to 15 gigahertz, with that being the kind of thing that is in or out depending on what the budget looks like on a given day. But certainly 10 gigahertz seems to be about the ceiling. That's being built now. Components of the project have gone out to different countries for delivery, and they're still thinking about the beginning of commissioning and science operations towards the end of this decade. A lot of this builds at least in the kind of core mid-frequency range around 1 gigahertz around the already operating Meerkat facility in South Africa. And so that's going to grow and develop into the SKA over time. So in some sense, the SKA is already operating, but it's not, it is not officially kind of built yet in the sort of core vision. So at this point, I'd like to say that's what the ngVLA is on the technical side. Let's turn around and think about the K-band in particular. And so I framed these thoughts by asking, well, what is actually in the K-band so far as the observatory goes? And really the major one that we've heard so much about are the redshift 0 spectral lines. So really ammonia, a bit on water, and all of these complex molecules have great reasons that you want to observe them in the K-band. But the GBT has also made some impacts in other parts of the science domain right here in the K-band, one of which is redshifted CO lines. Those are basically for redshift 3 to 4-ish galaxies. The ground state of CO redshifts into the K-band, and we can observe it and have actually observed it at the GBT. I mean, this very general sense of we. This is, I'll talk about that in a little more detail later. The pulsar continuum mechanism can reach up into K-band, but it gets extremely faint at that point. There's emission that's also very faint from the tail of the thermal dust continuum. And then we also have substantial radio continuum in here from Bremsstrahlung, so the thermal continuum emission from H2 regions. Notably compact H2 regions really show up in the K-band. And we also have anomalous microwave emission, which I always think of as the spinning dust emission, but this unexplained, not completely understood component of the dust spectrum that really peaks up around 30 gigahertz. We have a set of radio recombination lines. So these are, ions that are recombining in to form hydrogen and other species undergoing recombination in ionized gas. And the lines in the K-band are present and display a little less in the way of non-thermal departures than the low frequency lines. And of course, regrettably, we're also going to get more RFI here in the K-band. Basically, anywhere that the atmosphere is transparent, we're going to probably be thinking about RFI in the next 20 years. So there will probably be more satellite broadcasts coming down in the K-band, as well as a lot of ground-based applications will be cropping up here. So given this, like what we can see in the K-band, I want to pivot back to the ngVLA and talk about the key science that the facility is anticipating going, viewed specifically through the lens of the K-band. So the science goals of the ngVLA are framed up around these key science goals, one of which, the first of which is unveiling the formation of solar system analogs on terrestrial scales. This is really focusing at thermal dust emission at very high resolution towards forming stars and stellar systems. And so the main way that the K-band will crop up here is when you get to the brightest, highest column density protostellar disks, they can become opaque in the dust continuum at their centers. And if you drop down in frequency, the opacity drops off because the optical depth of the dust drops off. And so that allows us to actually get a mass sensitive tracer that drops down lower. Normally, this kind of argument is seen up at higher frequencies, but the more extreme cases apply here in the K-band. One that really is core to the K-band is the probing of these initial conditions of planetary systems with life and astrochemistry. I think that I am probably one of the least suited people to speak to this sitting here in this conference. So I will rely on my colleagues to correct me. But really, we've seen some wonderful demonstrations of what the K-band can do and why you really want to operate here for the discovery of molecules, and then what the ngVLA will enable, which is really the mapping of rare species. The third science goal is charting the assembly of galaxies over the course of the cosmic time. And here, this can grab a lot of the core K-band science that we're used to. We can study the dense gas in our own and nearby galaxies using ammonia and other tracers. We can also look at the AGN emission because it's bright across the spectrum here. We can look at redshift CO to study the molecular gas content of distant galaxies and how the gas was being built up over the course of time. And we also study redshift 0 water megamasers, so finding them, and then ultimately with the ngVLA sort of mapping them out to do, for example, trigonometric parallaxes to, direct distance determinations to distant galaxies using the high resolution capabilities of the facility. Another case where the K-band really shines in the ngVLA is using pulsars in the Galactic Center. And here the idea is that you're looking for these millisecond pulsars close to the galaxy, the supermassive black hole, and use those as a test of general relativity and measuring the properties of the supermassive black hole in the Galactic Center. Now, ordinarily, you would want to do this at low frequencies because the pulsar emission mechanism is really bright there and then drops off with frequency. But because of interstellar scintillation and scattering, you just don't get as much light. And looking at higher frequencies, you should be able to sort of see through the mist and get a better perception. So the K-band is about the sweet spot where scintillation and dispersion are down, while the emission mechanism is also down, but it's enough that we should be able to measure the millisecond pulsars using the K-band here. So it's one of the main areas where we see that kind of 20 to 30 gigahertz becoming really important. And then finally, the last science goal for the ngVLA is studying the evolution of black holes through transient events. And here, this is a grab bag across the electromagnetic spectrum to try to understand these facilities. But really, and so the K-band joins with all the other great observing bands that are being used to kind of understand these transient events and sort of see their emission mechanism over time. And there are times when that 20 to 30 gigahertz window is really the ideal time to probe the conditions here. So that gives a lens through which the ngVLA is doing the science. And I want to come back to some of the ones that really focus on where the ngVLA is going to operate in spaces where the Green Bank telescope has already had some really great demonstrated scientific successes. And I think the very first one is going to be mapping of ammonia in the Milky Way. We hear a lot about this at this conference. I love all of this stuff. It's simply the best science. But what we've been seeing is that we can observe ammonia lines in parallel with a lot of other common species in the K-band, like formaldehyde and methanol. Here. And so what we see is the advantage you get by building interferometer data is the details. So this is a map from NGC 1333 from the gas data, and you can go back and there's been a concerted effort led by Shea Storm back in the middle of last decade to map this region with the VLA, and sunk in a substantial amount of time to build up these resolved maps of what the high resolution structure is. Because as we've heard a few times today, the low resolution Green Bank telescope data does not capture everything that's going on in terms of the telescope beam. There's still structure all the way down here. Even so, we put in a lot of effort to get these data, and they are not deeply, amazingly, beautifully inspiring. You put, several tens of hours with the VLA to get signal to noise of, tens of data, which starts to look challenging to actually do a lot of the beautiful kind of parameter mapping that we saw earlier today. So this is an example of our spectra where we start to get about 4 Kelvin peak emission, but still substantially noisier, or still quite noisy. When we think about this in the context of the ngVLA, we take one of these fields, which took about 4 hours all in at the VLA to get the observations that I just showed you. The ngVLA is going to have the primary beam sort of depicted by this red circle here, and it'll be kind of an hour per field, down from 4 to get down to higher resolution data. And that's the thing when you look at the ngVLA is that it's better, and you're going to do really good for a lot of this thermal science, but it's only an order of magnitude better. This is not kind of clicking into place with this like, wow, this is this amazing new view of the interstellar medium, because what we're seeing is essentially we'll be able to push out just a little bit farther and get kind of Gould belt style studies out to slightly farther away targets. It's not going to turn into this efficient wide area ammonia survey machine. It's still going to take time to really get down and do those observations. What it will do is it will have all the lines. And so I took the ammonia rotational diagram here, which is coded in like JK tracers, and we normally study these metastable transitions here, where JK equals 1, 1, 2, 2, 3, 3, here plotted in terms of their equivalent temperatures. But we will get all of the excited lines, and you can see it's often worth trying to understand ammonia in context of how well these rarer, fainter lines are excited up here, because they'll undergo rotational transitions, which will drop them down the ladder, which is why most of the ammonia hangs out in the bottom states here. But nonetheless, you can see the 2, 1 line, for example, can be significant and really help you construct constrain what is the level distribution and therefore the temperature of this gas. One thing that opens up with the ngVLA is extragalactic capabilities. Right now, you can, like, the difference here is between hundreds of hours on the GPT, or sorry, on the VLA, and tens of hours on the VLA. One is a large project. The other one is something that you can conceivably ask for and not have the TAC laugh you out of the room. An order of magnitude matters a lot, because then you can start to do these kinds of studies in distant galaxies, or in, sorry, not distant galaxies, in distant regions that are nonetheless in nearby galaxies. This is your news flash for the day, is that the Milky Way is really pretty close, and everything that we're studying is close. And the second that we want to pivot to another galactic system, incredibly far away. So what I did here is I took the Cygnus X data from the Keystone project and basically averaged over this 50 parsec region down into a single spectrum. And then I said, what would I see if I observed that spectrum for 20 hours towards one of my other favorite galaxies, which is M33, you know, reasonably distant galaxy, but still almost a megaparsec away, versus this kind of region, which is hanging out at a kiloparsec away. We ultimately cannot get away from the fact that stuff in the Milky Way, just because it's so close, is always going to give us the most detailed, high-resolution view of star formation. And putting 10 times as many dishes on the ground isn't going to change that. We're never going to overcome that 1,000 times farther away in distance. So this comes to harsh reality time about thermal surface brightness science. We just, we can't really get that much. So if we return to this radiometer formula and think about it in terms of thermal fluctuations, what we see here is that the thermal fluctuations depend on the size of the solid angle of the beam, this omega beam. So I like to think of this as, if we improve the sensitivity of the facility by a factor of 10, then the beam can be smaller in area by a factor of 10, or in angular resolution by a factor of about 3. So that means we can do the same science we do now with the VLA or the VLA and the GBT, but we can go a little bit farther away, 3 times farther away. That doesn't get us to nearby galaxies. So that's the rule is that there's still going to be a lot of relevance for studying the Milky Way, and the ngVLA will not change that. The other thing that really came up a bit is about astrochemistry. I am not going to pretend to be an expert on this. You have, I believe, one sitting in the audience who brought all the grads, like you have several sitting in the audience, I should, but this is Brett McGuire's paper that I stole liberally from to give you this slide. Ask Brett, he can fill in all of the details. But this is a paper where we found this propylene oxide molecule using GBT and Parks. And this is a chiral molecule. So we have this basically a mirror image version of the propylene oxide that's also present in the interstellar media. And this is interesting because when we think about chirality of molecules, so especially these targeted molecules that may be important for life, then we end up with molecules of 2 different chiralities. And the cool thing about life is it only interacts with one. So all of our biochemistry processes and amplifies one family of molecules, even though if you just take the same random group of molecule atoms, throw them together, form this molecule, you can get a mirror image of it, this opposite chirality molecule, your levo versus your dextro. What's happening is you only generate one through the process of life. So one of the hallmarks of biosignatures will be to find a molecular species where there is far higher dominance of one chirality of a molecule versus another. And this is observationally detectable using circular polarization. So if we have polarization capability paired with these line observations, we really have a good way of sort of finding biosignatures through these complicated molecules. Again, I'm just the messenger here, and I'm really, but I thought this was fascinating, so I got really excited about it. But this was a figure of merit that was put into some of the key science goal papers, I believe created by Brett as well, but showing that we saw these wonderful things about the GBT, but we're at this point of diminishing returns. And the point here is that an order of magnitude really does buy you a lot in terms of getting down to some very interesting species from the prebiotic chemical perspective. So I think that this is a good opportunity in the K-band for the ngVLA. And because I'm going to do the worst thing that a human can do, which is basically say there's also a study of high redshift CO. Basically the GBT did a lot of high redshift CO 1 to 0 detections. Sort of the gravity of the field that seems to have sort of pulled over and focused a bit on ALMA in the past several years. But the ground state of CO 1 to 0 sits in the K-band, and that's less significantly affected by excitation effects. I'm just going a little quick because I realize I've run low on time. And I wanted to comment a bit on the GBO sitting inside an ngVLA future. And I see that there's two complements of scientific complementarity and technical complementarity and opportunities for GBO and the data that have come from and are going to come from the facility. I think the first key thing to recognize is that the GBT exists and the ngVLA is still at least a decade plus in the future. So there's an ample amount of science that's going to be basically pathfinder, groundbreaking science that is going to come out of operating in the K-band at GBO that will never change, and it will set the stage for exciting stuff with the ngVLA, but the new facility is not going to be an adequate replacement for having this large single dish capability. We can think about technical capabilities where you can think about integration into the long baseline array, zero spacing capabilities, where even though there will be a total power component, having that in hand can really help help a science project out. Polarization capabilities, and the fact that the radio quiet zone also is going to provide some mitigation against RFI for this. And I'll close out by kind of returning to this idea of what the collecting area of the facilities are as a function of frequency. And I can put the GBT onto this area. And this is still like ngVLA. It's kind of this amazing facility for kind of single pointing science. But K-band has a focal plane array on it at the GBT now. And if you are trying to go over wide areas and do mapping, you get 7 GBT dishes out of that. And so suddenly this is looking like the facility that is able to provide a lot of the survey and groundbreaking science or pathfinding science for the ngVLA. So you can think about, well, what should we be doing with all of this, or an even broader, larger focal plane array? And I think there's plenty of opportunities. So we can simply push out the mapping that we've done. Nobody is going to say that our maps are complete and have covered all of star formation in the Milky Way or dense gas. We will get a little farther with the ngVLA, but we're not going to dramatically change the picture. And the GBTA mapping torus is going to be better than the ngVLA mapping anything at the Galactic Center or out in other galaxies. It's just you're constrained by your surface brightness sensitivity, and it's a harsh reality that we don't get that far there. The other thing I think is really exciting is that a lot of the data we've seen are entirely underexplored. We're not really pushing the limits on what we have done with the data. Like I've been involved with the gas and the Keystone teams, and there's still like at our first gas meeting, we wrote down like 30 papers we could write with the data. And we've got through maybe a third of them. There's still a list of 20 fantastic papers that could be written. And some of the great analyses that are coming out, I think Brian's talk's always super exciting and inspiring to see. And this really developed sort of approaches to more sophisticated analyses. It's an underexplored area. So I think I will say just briefly that one area where the GBT could be improved and really make a contribution is in the K-band radio continuum. The GBT is not necessarily the strongest instrument in terms of stability for continuum mapping, but this is also a vital kind of zero spacing contribution that's really hard to do. For example, with the ALMA model, the continuum zero spacing is still tricky to get into your data set. So here, the thermal radio continuum, if there was sort of a thought to improved instrumentation about that, there's some areas for development. So I apologize for running up against my time limit. I think that the ngVLA is going to be an order of magnitude improvement for interferometer science, and a lot of the science is going to flow through the K-band, but we don't necessarily see wide area mapping, continuum stability, or polarization studies really being readily supplanted by the ngVLA, and there's still a huge amount of stuff that can be done between now and the middle of next decade. So thank you very much. I appreciate you all listening in, and I'll field any questions.
Questions from Greenback? Do we have any online? Not yet. They're typing furiously. Jim, yes.
So I was interested to see your sensitivity comparison with the K-band focal point array. If we had a 100 pixel receiver, would that be a game changer in terms of mapping K-band emission?
I mean, it's a different, so yeah, yes, of course, who doesn't want
You have to
100 pixel
qualify
K-band? Am I preaching to the choir? Yes. But this is, but like I mean, they're different science use cases, right? But I think the point I wanted to communicate is that a 30 arcsecond beam on nearby structures is going to give us as much or more information than throwing tens of hours with the ngVLA at something far away. You're going to have, like, unless that object is unique, right? You need to be studying your supermassive H2 regions or the Galactic Center or things like that. But a lot of like the stuff that we've been focusing on very naturally fits into its, high resolution studies of star formation with a deep analysis of what the chemistry and kinematics are doing over, the complete census. Yes, like absolutely, that would be amazing.
Other comments? Anything coming in from abroad?